It was not recognized at all as being anything interesting when it was discovered. It was just a corroded lump about the size of a large D. Anything from ancient Greece simply shouldn't have gear wheels. These were precision gears with teeth about a millimeter long. Around 60 BCE, a ship was sailing through the straits between Crete and the Peloponnese. It passed the island of Antikythera, which had been known as a pirate hotspot just a few years earlier. Caught in a storm and unable to find shelter, the ship sank, taking the lives of at least 4 people. The vessel was likely a large merchant ship about 40 m long, carrying amphorae filled with wine and other goods, antique marble sculptures, bronze statues, glassware, and a small mechanical object made of wood and metal. This curious device, about the size and shape of a showbox, would have appeared to most as just a box of dials and gears. However, it was an analog computer capable of calculating cosmic cycles. This is the story of the Antikythera mechanism. The shipwreck's remains were discovered in 1900 by sponge divers from Symi while working off the coast of Antikythera, known in the ancient world as Aegila. One of the divers, Elias Stadiatis, dove to a depth of around 40 m. When he resurfaced, he was shaking, claiming to have seen dead, naked bodies lying on the seafloor. Captain Demetrius Kondos decided to investigate and found that the bodies were actually marble and bronze statues scattered across the ocean floor, along with numerous other artifacts. To prove what he had seen, Kondos brought up a life-sized bronze arm for the rest of the crew to see. Realizing the significance of their discovery, the divers began collaborating with the Greek government and archaeologist Georgios Iakovos to investigate the site. This became the first underwater archaeological excavation in history, and their findings were extraordinary. Alongside impressive bronze sculptures, divers recovered pottery from Rhodes and Asia Minor, Parian marble statues from the Aegean, glass artifacts from Syria, Palestine or Egypt, and coins made of silver and bronze from Ephesus and Sicily. The coins were minted between 76 and 67 BCE, suggesting that the shipwreck likely occurred sometime within the following decade or two. The variety of artifact on board indicated that the ship may have been a merchant vessel heading to Rome, though some scholars speculate it was carrying looted treasures. The divers brought up nearly 100 marble statues and bronze sculptures, including the famous Antikythera youth, which dates back to the 4th century BCE. These statues captured the public's attention and were celebrated as the most exciting discoveries. Over time, the findings became less impressive, but in the following year, a telegram reported the discovery of a slab with an inscription that could not be copied. At the time, no one realized this corroded piece of metal and wood would later be identified as the world's oldest analog computer. The slab was nearly discarded before reaching Athens, as the focus remained on larger, more visually striking artifacts. Unfortunately, because it was not treated for preservation after removal from the water, it suffered some damage due to exposure. The significance of the so-called Antikythera mechanism didn't remain hidden for long. In May 1902, the corroded object split into 2 pieces. Accounts of how this occurred vary, but visiting archaeologist Valeios Staris noticed a metal gear emerging from one of the sections, as well as inscriptions written in Greek. This discovery triggered over a century of research, revealing the true importance of the artifact. The initial cleaning and preservation of the Antikythera mechanism separated the slab into 3 pieces, and today it consists of over 82 fragments. 4 fragments contain multiple gears, while many others include ancient Greek inscriptions. To give you an idea of the scale and extraordinary precision of this mechanism, the largest gear measures only 13 centimeters in diameter and originally had 233 teeth. The level of craftsmanship here is hard to put into words. The first translations revealed the phrase ray of the sun, which led some researchers to believe it was an astronomical clock. This discovery shocked other scholars, who argued that such advanced technology couldn't exist until the 14th century, suggesting the device must have belonged to a much later ship. Over time, more details came to light. The Greek word for one of the ancient Egyptian months was identified, hinting at a solar calendar, while the Greek word for Venus, Aphrodite, suggested a connection to lunar movements. By the 1930s, researchers proposed that the mechanism could have been an astrolabe or a planetarium showing the sun, the moon, and the 5 planets known to the ancient Greeks. Research stalled until after World War II, when British physicist and science historian Derek de Soller Price took a deep interest in the device. Price noticed that much of the original mechanism was corroded into the fragments and suggested that it was used to calculate time cycles and astronomical events. He believed it wasn't made for seafaring but had simply been on a ship during its transfer to the intended owner. Price's persistence led to an important breakthrough in 1971, when nuclear physicist Charalambos Caracalos X-rayed the fragments, identifying 30 gears. Price attempted to reconstruct the mechanism based on the X-rays, but his version was complex and didn't match the delicacy of the gear teeth. It was still an impressive attempt, considering the challenge. In the late 1980s and early 1990s, researchers Michael T. Wright and Alan Bromley revisited the device with linear tomography to gain new insights. The most advanced studies began in 2005 with the Antikythera Mechanism Research Project in collaboration with the National Archaeological Museum. Researchers used CT scanning and polynomial texture mapping, now referred to as reflectance transformation imaging, RTI, to enhance the visibility of surface details. The CT scans were instrumental in revealing the internal mechanical structure of the fragments and even uncovered hidden inscriptions. These techniques also made visible inscriptions on the gears and other metal pieces much clearer. So far, about 3,000 of the estimated 15,000 characters have been transcribed. Researchers believe they have recovered approximately 30% of the original mechanism. All of the work and further research from this imaging has significantly improved our understanding of what this mechanism was used for and how it functioned. So let's get into it. The Antikythera mechanism essentially acted as an analog astrological computer. If you're unfamiliar with an analog computer, think of a non-digital wristwatch as a basic comparison. The mechanism was a box measuring approximately 30 centimeters high, 20 centimeters wide, and 10 centimeters deep. It featured rectangular bronze plates on the front and back faces and was enclosed in a wooden casing. A knob on one side controlled the internal gears. The front face displayed a circular dial surrounded by two concentric rings with different scales of measurement. The inner ring was fixed and divided into 12 sections, each marked with a zodiac symbol. Each section contained 30 evenly spaced ticks, reflecting Babylonian astronomy where 1/12 of the ecliptic, the sun's path around the Earth over a year, was equally assigned to each zodiac sign. This design allowed the mechanism to predict eclipses using the ancient Babylonian Saros cycle, which spans 223 lunar months, or just over 18 years. The second ring was removable and rotatable, marked with the months and days of the Egyptian calendar written in the Greek alphabet. This calendar had 12 months of 30 days plus 5 additional days at the year's end. Since the Egyptians did not observe leap years, their calendar drifted through the zodiac over about 120 years. This is why the ring had to be adjustable, accounting for the shifting alignment of the calendar with the zodiac. The front dial also included multiple pointers extending from its center. One was a lunar pointer that displayed both the position and phase of the moon. A small half-black, half-white ball attached to this pointer rotated alongside the dial, visually representing what the moon would have looked like. This mechanism accurately followed the moon's accelerating and decelerating elliptical orbit using epicyclic gearing, the first known instance of its kind. Additionally, the dial included a solar pointer, which showed the sun's position on the ecliptic and possibly the day of the year. Here, it also depicted the orbits of the 5 planets known to the ancient Greeks at the time: Mercury, Venus, Mars, Jupiter, and Saturn. The backside of the mechanism had 5 dials, 2 large spiral slots inscribed with scales and radial dials, and 3 smaller circular dials with small pointers. The top spiral is known as the Metonic dial, divided into 235 sections. Each section represents a lunar month and includes the Corinthian names for the months. This aligns closely with the 19-year Metonic cycle, where the lunar phases repeat at the same time of the year. The Callipic cycle, which spans 76 years, was also part of the system. This cycle is essentially a longer version of the Metonic cycle and helped convert lunar and solar years within the mechanism. The bottom spiral was similar but simpler, used to predict the time and day of eclipses in addition to the month. Whoever operated the mechanism had to carefully reset the pointers by lifting the pin and repositioning it at the start of the spiral once the pointers reached the end. The game's dial is another key feature on the back. It's the only pointer that moves counterclockwise and was used to calculate the timing of the Panhellenic Games, including the Olympics, Isthmian Games, Nemean Games,